работает. Сейчас посмотрим. Ага, замечательно. Раз. Замечательно. Звук есть. Okay, so let's recall that the previous lectures we proved two forms of the spectral theorem. The first form is the functional modal theorem, which states that every normal operator on a Hilbert space is unitarily equivalent to a multiplication operator acting on the big-O2 space for a suitable measure space. And the second form of the spectral theorem was proved at the previous lecture. It states that every normal operator has a Borel functional calculus. So formally, these two forms of the spectral theorem are different. Formally, they are not equivalent to each other. But in fact, each of them gives us some useful information about the operator. And actually, they can be deduced from each other. By the way, it's a nice exercise. I forgot if I included it into the exercise sheet. But it's a nice exercise to deduce the Borel functional calculus theorem from the functional modal theorem. This can be done not in full generality, but for operators. I mean, in the operator form, I mean that the respective result about representations is not immediate, but for normal operators, this is indeed possible. I mean, it is possible to deduce the Borel functional calculus theorem from the functional model. Okay, so now today our main goal for today is to prove another form of the spectral theorem, which describes normal operators in terms of spectral measures. First of all, suppose that T is a self-adjoint operator on a finite dimensional Hilbert space. Of course, we know that in this case, T is diagonalizable in a suitable orthonormal basis. And the fact that T is diagonalizable can be equivalently written in the following formula. So T is the following sum, where lambda runs over the spectrum, and E lambda denotes the orthogonal projection onto the respective eigenspace of T. Of course, the sum is finite because the spectrum is finite. So this formula is easily seen to be equivalent to the fact that T is diagonalizable. Now, suppose now that H is arbitrary, but T is compact. T is a compact operator on the Hilbert space H. In this case, we have the Hilbert-Schmidt theorem. Which easily implies that essentially the same formula holds for T. Where E lambda are the same as before. So they are the orthogonal projections onto the eigenspaces. This is actually essentially equivalent to the Hilbert-Schmidt theorem. Okay, but of course now the sum is not finite. It is countable in general. The spectrum of a compact operator is at most countable. So in general, we have in general, this formula means the sum of a convergent series in B of H. And now let's suppose that T is an arbitrary self-adjoint operator on a Hilbert space. An actual question is, can we write a similar formula for T? And it's easy to see that in general the answer is no. The reason is that in general a self-adjoint operator on the Hilbert space has, of course, there can be some eigenspaces, but in general it can happen that there are no eigenspaces at all. And the simplest example is the multiplication by the coordinate on the L2 space on the interval. So this operator is self-adjoint, but it has no eigenvectors, eigenvalues, and so no eigenspaces. And so the right-hand side of this formula is just 0, and the formula fails. So roughly, our goal will be to show that we can save this formula if we replace here the sum by the integral. Of course, here U of lambda are no longer projections onto the eigenspaces. This is something different. So our goal for today will be to give a precise meaning to this formula, to explain what E of lambda is and what the formula means, and to prove this formula. Okay, so this was some motivation. Let's now discuss some simple facts about orthogonal projections. So suppose that H is a Hilbert space. By definition, a bounded linear operator P on H is an orthogonal projection orthogonalный проектор in Russian. If there exists a closed vector subspace H0 of H such that P restricted to H0 is the identity map and P restricted to the orthogonal complement is 0. Well, since H is exactly the direct sum of H0 and H0 orthogonal, we see that this definition can be written as follows. This means precisely that P is a projection, which means that P squared equals P, and the kernel of P is orthogonal to the image of P. This is the image. H0 is the image, and the orthogonal complement is precisely the kernel of P. We have the following useful algebraic characterization of orthogonal projections. I claim that P, a bounded linear operator P on H, is an orthogonal projection, even only if it satisfies the following algebraic identity. So P is an orthogonal projection, even only if it is a self-adjoint idempotent. Idempotent means that P equals P squared. An orthogonal projection is the same as a self-adjoint idempotent. To prove this result, let's first of all let's observe that P is a projection, if and only if P star is a projection. This is clear because, well, P star squared is the square of P star, is the joint of P star. This observation implies that, so now suppose that P is a projection. So now we want to show that P is orthogonal if and only if it is self-adjoint. Suppose that P is a projection, and we want to show that P is orthogonal if and only if it is self-adjoint. Well, P equals P square, P equals P star, if and only if these two operators have the same kernel and the same image. This is clear because each of them is a projection. And two projections are equal if and only if their kernels are the same and their images are the same. Okay, let's now recall the following simple fact, which was proved some time ago, that for each bounded linear operator T on Hilbert space, the kernel of the joint T star is equal to the orthogonal complement of the image. And the closure of the image is equal to the orthogonal complement of the kernel. This is a very simple fact. The first formula is rather straightforward, and the second one is obtained from the first one by taking the orthogonal complements. So if we now apply this formula, let's denote this formula by 1, we see that relation 1 can be equivalently written as follows. The kernel of P is equal to the orthogonal complement of the image of P. This is the first equation. And the second one is the image of P is equal to, well, P star is, the image of P star is closed. The image of P star is closed because it is a projection. And so this is nothing but, oh, sorry, I forgot, where is it? T star, of course. A little typo here. The orthogonal complement of the kernel of T star. So the second formula means that the image of P is the orthogonal complement of the kernel of P. But these two formulas are now obviously equivalent to each other, and they mean exactly that the kernel. Okay, let's now introduce some notation. The set of all orthogonal projections on H will be denoted like this, PR of H. The set of all orthogonal projections on H. We now give the following definition. Suppose we have two orthogonal projections, P and Q. We say that they are orthogonal to each other, or just orthogonal. And we write the following symbol. If their images are orthogonal, this property can also be characterized algebraically as follows. Proposition 2. P and Q are orthogonal if and only if their product PQ is 0. And this happens if and only if QP is 0. And this is equivalent to say that P plus Q is also an orthogonal projection. And in this case, if they are orthogonal, the image of P plus Q is nothing but the direct sum of the image of P plus the image of Q. Well, this is a nice algebraic exercise for you. It's quite easy. Maybe the only not entirely trivial part is to deduce the orthogonality from this property. So if P plus Q is a projection, then P and Q are orthogonal. So a hint to this exercise, P plus Q squared equals P plus Q, that is, P plus Q is a projection, if and only if PQ plus QP is 0. Formally, this is weaker than this. So we want to deduce from here somehow that PQ is 0 and QP is 0. So a trick is to multiply this equality by P on the right, and then by Q by P on the right, and then by Q on the left. So multiply by P and then by Q. And so as a result, you will see that PQ equals QP, and so each of them is 0. Another useful property of orthogonal projections, proposition 3. Suppose that we have finitely many orthogonal projections on H, and we assume that they are pairwise orthogonal. I claim that for each, well, let's also assume that they are non-zero. Assume they are non-zero. I claim that for each n tuple of complex numbers, lambda 1 to lambda n, the norm of the following linear combination from 1 to n is just the maximum of the absolute values of lambda i's. Well, this is also a rather easy exercise. Essentially, the exercise is based on the Pythagorean theorem. Well, a little hint. Decompose H in the following way. Here, HI is the image of the respective projection. And H prime is the orthogonal complement of this direct sum. And apply the Pythagorean theorem. Okay. Let's now introduce spectral measures. Suppose that we have a set X. X is a set. And A, script A, is sigma algebra of subsets of X. By definition, a finitely additive spectral measure, a finitely additive spectral measure on A is a map, let's denote it by E, from A to the set of orthogonal projections on H, such that E satisfies the following axioms. First, E is finitely additive in the sense that for any finite disjoint family of sets in our sigma algebra, we have the following equality. here A1 to AN are pairwise disjoint sets. So this is the property of finite additivity. We also require that E of X is the identity operator. And finally, property 3 is the following. You have two sets A and B, then E applied to their intersection is the product of E of A and E of B for each pair of sets A and B. Well, property 1 is the usual finite additivity property, similar to the respective property of positive measures. Property 2 is just the normalization. Property 3 may seem a little bit exotic because it almost never holds for positive measures or for complex measures. But in fact, because of the fact that E acts to the set of projections, it can be shown that property 3 follows from property 1. This is a useful exercise for you. We will not use this result, and we assume that 3 is an axiom. But actually, 3 can be deduced from 1. Well, let's look at some simple properties of spectral measures. Let's observe that, first of all, the finite additivity implies that E of the empty set is the zero operator. This is obvious. And property 3 implies that if A and B are disjoint, then the respective projections are orthogonal because their product will be 0 in this case. So they are orthogonal, but by proposition 2. Okay, let's now take an arbitrary finitely additive spectral measure, and let's construct a family of complex measure associated to E. So we introduce some notation. Suppose that E is a finitely additive spectral measure on A. We take a pair of vectors, U and V, and H, and we define a complex measure E U V on the same sigma algebra by the following rule. We take the projection E of A, apply it to U, and take the inner product with V. So clearly this is a finitely additive complex measure. A finitely additive complex measure. Proposition 4, I claim now that the variation of this measure is finite. So this number is finite. In general, the variation of a finitely additive measure is not necessarily finite. But in this case, it is finite, and moreover, it satisfies the following inequality. Well, to prove this result, let's take an arbitrary decomposition of X into finitely many pieces, into finitely many disjoint pieces. So we suppose that X is the following disjoint union. And let's try to estimate the following sum. By the way, let's recall the variation, the left-hand side of this inequality. By definition, this is the supremum of all such sums, where the supremum is taken over all decomposition of x of this form. So in general, this supremum can be infinite. But in this case, it will be finite. And to prove this result, we do the following trick. First of all, we replace here the absolute value by the following number. So basically, we remove the absolute value and include here a suitable factor of absolute value 1. So lambda I is a complex number of modulus 1. So now, by definition, this is the sum of lambda I E of AI applied to U, and then we take the inner product with V. So now we write this in the following form. Just by linearity of the inner product for the first variable. And apply the Cauchy-Brunikovsky-Schwarz inequality, which implies the following estimate. And now we use proposition 3. So these projections E of AI are pairwise orthogonal, because our sets are disjoint, so these projections are pairwise orthogonal. And by proposition 1, proposition 3, this sum is precisely the maximum of the absolute values of lambda I, but this is 1. And so this is less than or equal to the norm of U multiplied by the norm of V. And this completes the proof. Okay, let's now look at some examples of spectral measures. Example 1. Suppose that we have a measure space, X, A, mu, a measure space, not necessarily finite, not necessarily sigma finite, an arbitrary measure space. And let H denote the big L2 space, L2 of X mu. And we define the spectral measure on A as follows. E of A will be the multiplication operator by the characteristic function of A. So here, high A is the characteristic function, or the indicator function of A, which is 1 on A and 0 elsewhere. So clearly, all axioms are satisfied, so E is a spectral measure. And example 2, which in fact generalizes example 1. Well, again, we suppose that we are in this setting, so we have a set and a sigma algebra of subsets of X. And we denote by B sub A of X the algebra of bounded measurable functions. Bounded, measurable, or more exactly, a measurable functions on X. Well, probably I keep the definition of the spectral measure. So now we suppose that we have a star representation of this algebra. Let pi be a star representation of this algebra on the Hilbert space H. And now we can define a spectral measure by the following formula. Again, it's rather easy to see that all axioms are satisfied, so E is a spectral measure. On A. In particular, property of 3 follows from the fact that the characteristic function of the intersection is the product of the respective characteristic functions. It turns out that example 2 gives us the general picture. So any spectral measure appears like this. So we have the following result. This is theorem 1. Suppose that we have a finitely additive spectral measure, E on A. A finitely additive spectral measure. I claim that then there exists a unique star representation, pi, or we'll denote it by E, IE, of the algebra of bounded measurable functions on X, such that I and E are related by this formula, such that IE applied to the characteristic function of any set is just E of A for all A. So in other words, we see that the correspondence between spectral measures on A and star representations of the algebra of bounded measurable functions, so these sets are in bijective correspondence. And moreover, we have the following useful formula. For each bounded measurable function f on X, if we apply our representation to f, so this is an operator, apply it to U, and then take the inner product with V. So this number is nothing but the integral of f with respect to the complex measure E, U, V. And this holds for each pair of vectors U, V, and H. So note that the right-hand side here is well defined, because E has finite variation. And we discussed some time ago, this was in the previous term, but anyway, it's a rather standard fact that any bounded measurable function can be integrated against any complex measure of finite variation. Okay, and before we prove this result, let's introduce the respective terminology. The operator IE of f is called the integral of f with respect to E. And this operator is denoted in the following standard way. Which is quite compatible with this formula. Okay, so to prove this result, we first define our representation on the algebra, on the subalgebra of simple functions. So we let SA of x denote the linear span of characteristic functions of measurable sets. The algebra of A simple functions. It's well known from measure theory that this is a dense subalgebra in B of x. SA of x is a dense subalgebra of B of x. This is quite standard. Each bound of measurable functions is a uniform limit of simple functions. We now take any simple function f and observe that we can write this function in the following form. It's a finite sum, finite linear combination of characteristic functions of measurable sets, where we can assume that the sets are disjoint. So Ci is a complex number, Ai are measurable sets, and they are pairwise disjoint. Again, this is more or less standard. And now we can define our operator, i.e., our representation, by the following simple formula. Well, formally, we have to show that this is well defined, that this doesn't depend on a specific choice of such a representation. But this is rather standard, and I leave this as an exercise for you. I.e. of f is well defined. This is proved in exactly the same way as for the usual Lebesgue integral of simple functions with respect to the positive measure, So in this case here, there is no difference between spectral measures and positive measures. This result is proved in exactly the same way. And second, the second exercise is that the resulting map, IE, which is defined on the algebra of simple functions, is indeed a star representation. It is easily seen to be linear, and the multiplicativity of this map follows from axiom 3 of spectral measures. So E of the intersection of A and B is the product. Is the product of E of A and E of B. So this formula implies that IE is multiplicative. So it is a star representation. Okay, and now since SA of A is dense in here, we simply extend it by continuity. Of course, to extend it by continuity, we have to know that it is continuous or equivalently bounded. Well, let's show that it is bounded. The norm of the respective operator, IE of f, so this is the norm of this linear combination. Again, we use proposition 3. So E of AI are pairwise orthogonal projections. So by proposition 3, this can be estimated as the maximum. Actually, this is exactly the maximum of the absolute values of Ci. Well, this is less than or equal because some of the projections can be 0. Some of these projections can be 0, so this is less than or equal to the maximum of these absolute values. But this is nothing but the uniform norm of f. If we look here, and if we recall that the sets are disjoint, we see that this is This is exactly the uniform norm, the supreme norm of F. So we conclude that IE is bounded, and now we can extend it by continuity. It uniquely extends to a star representation of BA of X. So this formula holds by construction. And now finally we have to prove that this equality holds. But this equality obviously holds if f is a simple function. So let's denote it by 2. 2 holds for the characteristic function of any measurable set, just because of this. So by linearity, it holds for any simple function, for each simple function f by linearity. And finally, by continuity, it holds for each bounded measurable function f. And this completes the proof. So in summary, we get a one-to-one correspondence between finitely additive spectral measures on A and star representations of the algebra of bounded measurable functions. There is a bijection between these two sets. Okay, and now let's apply this correspondence to the Borel functional calculus for a normal operator on a Hilbert space. So we know that the Borel functional calculus sits here. So this is a star representation of the algebra of bounded Borel functions. But moreover, we know that the Borel functional calculus has the extra property of being continuous with respect to the weak measure topology here and the weak operator topology here. So this is not just a star representation, it is a star representation which has this extra property of continuity for these two topologies. So it is now natural to ask which spectral measures correspond to star representations having this extra continuity property. And here's an answer. So from now on, we suppose that X is not just a set, but is a compact Hausdorff topological space. Compact Hausdorff topological space. We consider the Borel sigma algebra on X. And we give the following definition. So we suppose that E is a spectral measure on the Borel sigma algebra. A spectral measure. And we give the following definition. We say that E is regular if all the respective complex measures E, U, V are regular. That is, they are random measures on X for each U and V. So E is regular if all the respective complex measures are regular. That is, they are sigma additive radon measures. And we have the following result, theorem 2. I claim that E is regular if and only if the respective representation, that is the integral with respect to E, which is a representation of the algebra of bounded Modal functions on X, is continuous for the weak measure topology here and for the weak operator topology here. So star representations having this extra continuity property correspond precisely to regular spectral measures. Well, first of all, let's prove the left to right implication. Suppose that E is regular. So we take any bounded Borel function f. We apply our homomorphism, i.e. to f, and we calculate the respective semi-norm determined by a pair of vectors u and v on H. So this is one of the semi-norms here, which determine the weak operator topology. So by definition, this is the absolute value of the following number. But what is this? In theorem 1, we proved that this is nothing but the integral of f with respect to the measure E, U, V. But what is this? This is one of the semi-norms on B of X from the family which determines the weak measure topology. This is the semi-norm of f corresponding to the radon measure E, U, V. So now we know, we have assumed that this is a radon measure. So this is one of our semi-norms. And this equality implies that IE is indeed continuous for these two topologies. Okay, let's now prove the right to left implication. So now we suppose that I is continuous for these topologies, and we want to show that E is regular. So let's explicitly write the continuity property of this operator in terms of semi-norms. So we recall once again the continuity criterion for a linear operator between locally convex spaces. So we see that for each semi-norm here, so for each pair of vectors U and V in H, there are finitely many semi-norms here. There exists finitely many measures, radon measures mu1 to mu(n) on X. And there exists a positive constant C such that the following estimate holds. And this estimate holds for any bounded Borel functions, for any bounded Borel function f on X. This is just a continuity criterion for a linear operator. Okay. We want to prove two properties of the respective complex measures EUV. First of all, they should be sigma additive, and second, they should be regular. So first of all, let's prove the sigma additivity of EUV. suppose we have a chain, an increasing chain of Borel sets. An increasing chain of Borel sets, and let B be their union. So the sigma additivity of this measure is equivalent to the equality that E of B is the limit of the measures of BI. Well, let's look at the characteristic functions of the respective sets. I claim that I have the following convergence for the weak measure topology. This follows, for example, from the Lebesgue dominated convergence theorem. They converge pointwise, and they are bounded by 1. So we have the convergence for the weak measure topology. But since our operator are continuous, we conclude that the respective measures, spectral measures E of BI, converge to the spectral measure of B for the weak operator topology. And so they converge with respect to every semi-norm, which determines the weak operator topology. So for each pair of vectors U and V and H, we have the following convergence. But this means exactly that EUV of BI converges to EUV of B. And so this implies that our measure is sigma additive. EUV is sigma additive. Okay, and now let's prove the regularity of EUV. So we look at this estimate, and let's substitute here for f, we substitute the characteristic function of any measurable set for any Borel set. In this formula 3. Then the left-hand side will be EUV of B, the absolute value of EUV of B, and the right-hand side will be C times the maximum of the absolute values of mu I of B. And this can be estimated as C times mu of B, where mu is the sum of the variations of the measures mu I. So each mu I is regular. The variation of a regular measure is obviously regular, and the sum of finitely many regular measures is regular. So this is Radon measure, mu. But if we recall now the definition of a Radon measure, of the regularity property, we easily see that if a sigma additive measure, if a complex sigma additive measure is dominated by a regular measure, in this sense, then it is itself regular. So this inequality easily implies that EUV is also a Radon measure. And this completes the proof. Okay, we can now combine theorems 1 and 2, and we get another form of the spectral theorem. This is Theorem 3, which describes star representations of algebras of continuous functions in terms of spectral measures. Suppose that X is a compact Hausdorff topological space. H is Hilbert space. And pi is a star representation of C of X on H. A star representation. I claim that there exists a unique regular spectral measure E on the Borel sigma algebra of X such that for each continuous function f on X, pi of f is nothing but the integral of f with respect to E. So representation, star representation of C of X bijectively correspond to regular spectral measures. And moreover, in this case, for each bounded Borel function f on X, the canonical extension of pi tilde, so pi tilde is the canonical extension of pi to B of X. This is the unique extension which is continuous for the weak measure topology and the weak operator topology. Pi tilde of f is given by the same formula. The proof is just a combination, essentially a combination of theorems 1 and 2. We already know that pi tilde exists from the previous lecture. So we just define E by the following formula for each Borel subset of X. So theorem 2 shows that E is a regular spectral measure. Is a regular spectral measure. And the uniqueness part of theorem 1 shows that pi tilde is nothing but the integral with respect to E. So we get this formula, and the fact that this property for continuous functions uniquely determine E follows from the fact that the correspondence between pi and pi tilde is bijective. The uniqueness of E follows from bijective correspondence between pi and pi tilde. I mean that star representations of C of X bijectively correspond to those star representations of B of X which are continuous for the weak measure topology and for the weak operator topology. And that's it. So this gives us the required spectral measure. And let's now finally apply this to normal operators. If we apply this to normal operators, then we get theorem 4, and this is, let's call it spectral theorem 3. Suppose T is a normal operator, a bounded normal operator on a Hilbert space H. Then there exists a unique regular spectral measure E on the Borel sigma algebra on the spectrum such that T can be written as the following integral. Over the spectrum. And moreover, this formula can be generalized, namely for each bounded Borel function f on the spectrum, the Borel functional calculus for T, that is the operator f of T, is given as the integral of f with respect to E. Theorem 4 is a special case of theorem T, of theorem 3. We simply apply theorem 3 to the continuous functional calculus. Apply theorem 3 to the continuous functional calculus. And again, the uniqueness of such a measure follows from the fact that that normal operators whose spectrum belongs to a fixed compact subset of the complex plane bijectively correspond to star representations of the respective algebra of continuous functions. Well, this form of the spectral theorem, at the first glance, it may seem a little bit exotic, because it involves spectral measures, which are quite mysterious objects. But I'd like to stress that this, essentially, this form of the spectral theorem is very close to the Borel functional calculus theorem. So, well, indeed, a little remark. If you have such a measure E, then just the other way around. If we have the Borel functional calculus for T, then we can reconstruct E from the Borel functional calculus by the following formula. So E of B is just the result of applying the Borel functional calculus to the respective characteristic function. Or in our notation, this is the result of applying the function chi b to our operator T. So if we have such representation, such a formula, then we can reconstruct the Borel functional calculus by using this formula. And the other way around, if we start with the Borel functional calculus, we reconstruct the spectral measure E by this formula. So this is essentially, well, maybe not exactly equivalent, but this is very close. This statement is very close to the Borel functional calculus theorem. And let's introduce the standard terminology. This formula is called the spectral decomposition of T. In some sense, this shows that T can be approximated by linear combinations of projections. Because if we approximate this function lambda, which takes lambda to itself by step function of this form, then we get an approximation of T of this integral by the respective finite sum, that is by the respective finite linear combination of projections. So this formula is called the spectral decomposition of T, and the respective projections in the range of the spectral measures of the spectral measure, the projections E of B, where B is a Borel subset of the spectrum. Projections are called the spectral projections of T. Now, in summary, the different forms of the spectral theorem, except for the functional modal theorem, can be illustrated by the following picture. Summary. We have the following bijective correspondences. If we take a compact subset of the complex plane, then we can consider the set of all normal operators on a Hilbert space H, such that the spectrum of T is contained in X. And this set bijectively corresponds to the set of star representations or the algebra of continuous functions on X. This holds for any compact subset X of the complex plane. So the correspondence is given by the continuous functional calculus. Now, as the previous lecture, we have seen that this set bijectively corresponds to the set of all star representations of the algebra of bounded Borel functions, which are continuous for the weak measure topology and the weak operator topology. Star representations of the algebra of bounded Borel functions. And moreover, this correspondence holds now not only for compact subsets of the complex plane, but actually for any compact Hausdorff topological space. And today, we have seen that this set bijectively corresponds to the set of all regular spectral measures. On the Borel sigma algebra. Again, X is a compact Hausdorff topological space. So this picture describes correspondences, describes relations between different types of objects, and the correspondences are given by the respective forms of the spectral theorem. The only form of the spectral theorem which is not in this picture is the functional modal theorem. And the reason is that this functional modal is not unique, not unique and not natural in any reasonable sense. So it is very convenient, but we cannot put it into this picture. Well, in conclusion, I say just a few words without giving any precise definitions. In fact, it can be shown that there exists a canonical functional modal for any normal operator. But to describe it explicitly, we will need the notion of a measurable Hilbert bundle, which I have no time to define. Nevertheless, I'd like to state this result without proof and without exact explanation of the ingredients. Theorem 5, let's call it Spectral Theorem 5, or Spectral Theorem 4. This theorem not only describes the structure of an arbitrary normal operator, but actually it also leads to a classification of normal operators in reasonable terms. So suppose that T is a normal operator on a Hilbert space, and here we have to assume that our Hilbert space H is separable. This is essential here. H is separable. Then there exists a positive random measure mu on the spectrum, and there exists a measurable Hilbert bundle, which I have no time to define. That's denoted by script H. Measurable Hilbert bundle over the spectrum, over sigma of T, such that T is unitarily equivalent to the multiplication operator, MT, acting on the space of square summable sections of this bundle, which is usually denoted by gamma 2. And the multiplication operator is given by the same old formula. If little s is a section of this bundle, then the operator acts by the following formula. For example, if our operator is cyclic, then it turns out that the respective Hilbert bundle is trivial and one-dimensional, so the space of square integrable section is just the little L2 space, on the spectrum, and we get our functional model for a star cyclic normal operator that was proved some time ago. So in the general case, we have to replace the L2 space on the spectrum by the space of square integrable functions of a suitable measurable Hilbert bundle. And moreover, if I have two such operators, moreover, if T and T prime are two normal operators on different Hilbert spaces, then they are unitarily equivalent, if and only if, first of all, their spectra are the same. Second, the respective measures are equivalent in the sense of Radon-Nikodym. And finally, the dimensions of the fibers of the respective bundles are the same, almost everywhere. By the dimension, I mean the usual dimension if it is finite dimensional, and infinity if it is infinite dimensional. Here, the separability assumption is essential because of the separability, there can be only one infinite dimensional case where the respective space is isomorphic to the little L2 space. And this is the full set of invariants, of unitary invariants of a normal operator. So the triple consisting of the spectrum, which is a compact subset of the complex plane, the measure mu, a positive Radon measure on the spectrum, and the so-called multiplicity function, which calculates the dimension of the fiber. So this triple is a full set of unitary invariants of a normal operator. So probably this is the best and the most useful form of the spectral theorem. But unfortunately, we have no time to prove it in detail and to explain what a Hilbert bundle is. Spectral theorem has many useful applications, and not only in functional analysis, but also in some neighboring fields of mathematics. In particular, the mathematical model of quantum mechanics is essentially based on the spectral theorem. Again, my original plan was to discuss some applications of the spectral theorem to representation theory, but again, unfortunately, we have no time for this. Anyway, one nice application, which is, in my view, is very nice, is given in our exercise sheet. Namely, by using the spectral theorem, we can prove that if we consider the algebra of bounded linear operators on a separable Hilbert space, then there is only one closed, non-trivial, closed two-sided ideal in BOH, namely the ideal of compact operators. So this is, in my view, this is a rather nice application of the spectral theory. Okay, thank you for coming, and that's all for today. And this was the last lecture. So next Friday we have an exam.